Hi Joshua, hello. Hi.
Hello.
So today we'll be discussing and give examples of the way to verify or prove trigonometric identities. Let us first discuss the different identities. First, we have the Pythagorean identities. You just need to memorize at least the basic Pythagorean, three basic Pythagorean identities, which are written in black. And then these the red ones are the derived identities. Okay, so by using the rules of transposition, you can get the other identities. Then we have the reciprocal identities. You just need to memorize the three basic reciprocal identities, and then you can use the rules for transposition and to get the red ones, which are the derived identities. And also for the quotient identities, uh, the basic ones are the ones in black. And here you can see that we can also say that tangent theta is equal to secant theta over uh, cosecant theta. The reciprocal of tangent is cotangent, so it is equal to the cosecant also over secant. Aside from the basic quotient identity that cotangent is cosecant theta over sin theta. So let's go to the next page. Here, I prove that cotangent theta, which is equal to sine theta, cosine theta over sine theta, is also equal to cosecant theta over secant theta. I will substitute the, the, the equivalent identities. Cosecant theta is 1 over sine theta, and secant theta is 1 over cosine theta. So it will become 1 over sine theta times cosine theta over 1, which would become, which would be equal to cosine theta over sine theta. And just to explain to those who do not know the rules, if it's from sine theta is equal to cosine 1 over cosine theta, we can say that sine square theta is equal to sine theta parenthesis to the power of 2, which is equal to sine theta times sine theta. And sine theta, as we know, is 1 over cosine theta. So 1 over cosine theta times 1 over cosine theta, which is another way of saying 1 over cosine theta parenthesis to the power of 2. And the proper way to write that one is sine squared theta is equal to 1 over cosine theta. In like manner, here from the definition that the reciprocal identity tangent theta is equal to sine theta over cosine theta, we will find out that tangent square theta is also equal to sine square theta over cosine square theta. And from the reciprocal identity, uh, one tangent theta is equal to 1 over cotangent theta. Tangent theta square theta is equal to tangent to the parenthesis to the power of 2, which is equal to tangent theta times tangent theta. And tangent theta is equal to 1 over cotangent theta. Therefore, it is tangent square theta is equal to cotangent square theta. And as an example of how to verify or prove an identity, here's our example. Cosine, the problem is cosine theta, secant theta, equal to or identical to cosecant theta plus secant theta all over cosine theta plus sine theta. So in order to prove or verify uh, trigonometric identities, we have to show that the both sides of the expressions will be equal. But in proving so, we are simplifying, but then we are not allowed to transpose any term to the other side. So here, I manipulated only the right side of the equation. So I substituted the values of cosecant theta and secant theta. Here's what I got. And then getting the LCD, it becomes cosecant theta plus secant sine theta all over sine theta cosecant theta all over cosine theta plus sine theta. And the division here becomes multiplication. So we invert the denominator and the numerator and the denominator will cancel out. We therefore got 1 over sine theta times cosine theta, which you can split into 1 over sine theta times 1 over cosine theta. And 1 over sine theta is cosecant theta, and 1 over cosine theta is secant theta. Therefore, proving that both sides of the equation are indeed identical. Or I can also see this problem as cosine the numerator times 1 over the denominator. And I substituted the values, and similarly, I got into this point where these are in here and this step, they are already the same. So both sides of the equation are truly identical. So now it's your turn to do some verification of proof or proving of identities, trigonometric identities question. Number 1 is tangent square theta over secant theta plus cotangent theta over secant theta.
So
Equals to
verifying
1.
and proving trigonometric identities can be as easy as these problems. So earlier we've discussed that if there's a square after the trigonometric function, it is, let's say in this example, tan squared theta is equal to tan theta squared. So we'll be using that a lot here. So let's begin. So first of all, we will convert all of these squared thetas into the said form.
You can begin from the top if you want.
Okay.
In order to save space. Okay.
Convert already. Theta. I'm just converting all of them into this function squared form already. So now earlier we've seen that there's a quotient identity, which is tangent theta equals sine theta over cosine theta. Also cotangent theta also equals cosine over sine theta. We've also seen the reciprocal identities for secant and cosecant. Those are 1 over cosine squared. So we will now substitute those values in. Sine theta over cosine theta. Okay, so now we will revert back to the original form, which is the function and then squared after it. So we'll just substitute sine squared theta. So now we will invert this main fraction, so we turn it to multiplication. Yes. So, times cosine squared theta over 1. Actually, it's not necessary, but I just put it there so you can see that I flip the denominator. So cosine squared theta over sine squared theta. So we have some stuff that can be cancelled between both in the numerator and the denominator. So we can cancel this out. We continue here. So what's left is just sine squared theta plus cosine squared theta equals 1. So earlier we also saw that there's a Pythagorean identity, which is apparently sine squared theta plus cosine squared theta equals 1. So we can just waste 1 equals 1. So this is correct. So also say this one, so for people who don't know how this happened. Okay, so we can also just expand it into tan theta over sec theta sec. I'll do the same other fraction. All right, again, we will use the quotient. So become sine theta and the reciprocals. Put it there so I don't have to put the ones that won't interfere here. Okay, so now we can And we can remove this main fraction, these main fractions. So it's will become start from safe space. So maybe I could just what if I just make this fraction bigger? I can just multiply this, so this will just become sine theta, cosine theta, cosine theta. Just merge it, and then multiply this by 1 over cosine cosine. So actually, it's going to be reverse. It will be cosine theta times cosine theta, but I just put cosine theta over 1 maybe. Okay, so there's a lack of space. Let's continue. Here, hopefully it's will fit. Again, like terms. I know, not like terms, but there are the same terms on the numerator and denominator, so we can cancel those. So this will just equal if we multiply the sine and then the cosine, we'll just turn again into sine squared theta plus cosine squared theta. So we also know that that's 1. It's also equal to 1. So this 1 equals 1 again. So it's also check. So we go. Problem 1's done.
Yes. Go to the next page for problem number 2. Number 2 is x. Number 2 is cosine theta is equal to sine theta cosine cosecant. And these equal.
And so now here this is much easier than the previous question, but we'll still do it. So by using the commutative property of multiplication, we can rearrange them. So I'll just rearrange this sine theta cosecant theta times cosine theta. You can also just actually, as we've seen, sine theta and cosine theta are reciprocal, so we can just put this all equals to 1. So we can just say cosine theta equals cosine theta times 1. So we will be so other than that, we can just do this. Go back to sine theta times 1 over sine theta. This will cancel out. And then again times cosine theta. So that will also become cosine theta times 1. Or actually 1 times cosine theta. So cosine theta is again equal to cosine theta. Is correct.
Okay. So let's go to number 3. That is pretty easy. Number 3 is cosine theta tangent theta is equal to sine. Is it equal to sine theta?
Okay, so think there are probably two, and there are two ways for doing this. So maybe I'll just separate them. So for the first part, maybe some blank. Okay, this is okay. So here we'll just use the quotient identities for the quotient identity for tangent theta. So it will be cosine theta times sine theta cosine theta equals sine theta. So this will just cancel out, and then of course we'll just break it out. Okay. So that will just be equal to sine theta equals sine theta. So there's actually probably a B to this. Maybe we'll be using the definitions of the basic trigonometric functions themselves. As we can recall SOHCAHTOA, so
right here,
so so sine O equals O opposite over height each hypotenuse. Okay, and then some missing line. And then C cosine equals A adjacent over hypotenuse. And then P tangent equals opposite, and then A over adjacent. So just use the definitions right now. So cosine, as we've seen, is A over H, or adjacent over hypotenuse. And then we'll multiply that by tangent. So that's just times opposites over adjacents, opposite over adjacent. So here, there's two adjacents again, and it's numeric in denominators and adjacent. We cancel that. That equals O over H. Hey, look at that. So there's opposite over hypotenuse. That's sine. So this is sine theta.
That's pretty easy there. That is very clever. Your two solutions are very clever. So let's go to the next page. So what number are we in? Number 4?
Yeah.
Number 4. Let's try to prove that cotangent theta plus tangent theta is equal to cosecant square theta plus secant square theta all over secant theta plus secant theta. Okay.
All right. So for some, this might look a little complicated, but this is actually pretty easy. So we'll break down this complicated part. So you see in fractions, let's say if we have an example, A plus B over C, that's just equal to A over C plus B over C. So I'll just do that. We'll just break it down like that. So cosecant, that's cosecant squared theta over secant theta cosecant theta plus secant square theta secant theta cosecant theta. Okay, so here is equal to, and I'll just summary. So here there's a cosecant square theta, so this is cosecant theta times cosecant theta. Let's cancel this, so it will just be cosecant theta. So now, as you can see, it just became cosecant theta over secant theta plus secant theta over cosecant theta. Although we're getting close, so now we'll just use the reciprocal identities again. So cosine theta will just become 1 over sine theta, and then over 1 over cosine theta. And then will just be added to the other one, just the opposite or reciprocal. 1 over sine theta. So now we'll just multiply it. There's also multiplication sign. So cosine, cosine theta, sorry, plus okay, so this is equals to cosine theta over sine theta. And then that just becomes, this one just becomes sine theta over cosine theta. Okay, so we have the quotient identities too. So we can simplify this as simply cotangent theta plus tangent theta. You see? So yes, on the other side, left hand side is also cotangent theta plus tangent theta. They're equal. So correct again.
It's very clever too. Let's go to the next page. What number are we in?
So 5.
5. Let's change the color to black. Prove that sine squared theta times 1 plus cotangent squared theta is equal to 1.
So this looks like a very neat identity actually. It's all equals 1. So earlier we also discussed that there's this Pythagorean, there are Pythagorean identities. So in this case, there's a perfect Pythagorean identity for this one. So 1 over, I'll just change the color. So 1 plus cotangent square theta, meaning that that's just cosecant square theta. So we can just do this. Sine squared theta, cosecant square theta. So equal to 1. Okay, so we've also seen that this is a this is a quotient identity, so we should be sine theta squared. Okay, for this also just equal to sine squared theta cosecant theta squared. So just turn it to this. It's supposed to be equal to 1. So sine squared theta over sine squared theta. Yeah, this definitely equals to 1. So this must be cancel. 1. 1 equals 1.
Okay. So next number. I'll change the color to black again. Number 6. Prove that cosine squared theta over 1 over 1 minus sine theta is equal to 1 plus sine theta.
All right, so here, as we can see, number 6. So cosine squared theta, which that is actually equal to 1. Wait. So the actual identity is just sine squared theta plus cosine squared theta equals 1. So you can just transpose, and then cosine theta will become 1 minus sine theta by sine squared theta. This will be all gone. So we can now use this identity, this new identity, to derive identity. Cosine squared theta is 1 minus sine squared theta. We'll be needing this 1 minus sine squared theta. So there might be people who say, how do we do this? So apparently there's another concept in algebra, that is a special product, that is a squared minus b squared. That actually equals to a minus b times it. Wait, I just move this. It won't fit. So
Here,
a squared minus b squared, a plus b. So we see here, this is actually a 1 squared minus sine squared theta. So we can actually turn this into the a squared b squared form. So a squared minus b squared minus a minus b, that's the form. So that will just be equal to a plus b. So here in this case, this is a, 1 is a, and then sine theta is b. So we can also expand this like this. We can use logic, or we can just use rigorous algebra. So this one is sine theta. Okay, this should be equal to 1 plus sine theta. And in fact, we cancel this because they're the same. Yes, so 1 plus sine theta is indeed 1 plus sine theta.
yes. Okay. Let's turn to the next page for our last problem. What number are we in? What do we? 7.
7.
We just change the color of the ink, the pen to black again. So prove that 1 plus sine theta all over cosine theta is equal to cosine theta over 1 minus sine theta. How do you prove this, Josh?
So again, this looks like a pretty neat identity. And then just as if they were just open. So now, again, we saw that in this previous problem, we have this. We'll be needing that again.
The difference of two squares.
So now, we will expand. So, okay. What the same thing? So 1 plus sine theta. Also again, we can relate this. So we saw that 1 plus sine theta is equal to 1 square, 1 minus sine square theta over 1 minus sine theta. So we can just substitute that. This is the a plus b. So we'll just turn this a plus b. A plus b equals a squared minus b squared over a minus b. It's like we're doing this the opposite of what we did.
It's, reverse, right? Nice.
We're just going to apply what we did earlier. There's like, looks like this, just the opposite. So now, 1 minus sine theta, again, we'll just turn back. So 1 versus 1 minus sine squared theta. Oh, wait, it's not written here. But earlier I showed that cosine squared theta is equal to 1 minus sine squared theta. It's a derived identity. So we can just turn this 1 minus sine squared theta into cosine squared theta. So we just retain this 1 minus sine, and it can be simplified is over cosine theta plus cosine theta. So this already looking like it, but we'll just prove. Okay, so this should be the opposite. So this should be 1 over cosine theta. Ah, okay. So there will be a cancel. Could be canceling this square and then just canceling this. So this equals to cosine square theta over 1 minus sine square theta. Sine theta. So yeah, so basically cosine theta over 1 minus sine theta is apparently cosine theta over 1 minus sine theta. So I think we proved it already. Yes.
Oh, nice.
Nice.
Thanks
Thanks for watching.